Maybe he had family, and now they were just waiting for him. I was like, no, I'm not coming back. How was the weekend? How you guys did? How you guys doing? Bored? Who said bored? Why? Didn't go anywhere at all? We didn't. Yeah, it's okay. I use a flamethrower.
Cool.
Yeah, that was pretty cool.
Where? At your house?
Well, it wasn't a flamethrower, but it was the closest thing I have seen to a flamethrower. So a friend of mine, he lives on a farm, and he had all the waste from trees and dead trees and stuff that he needed to burn. And he was like, well, let's have a bonfire, and they just go and drink and blah blah blah. And I thought he was just to start the bonfire. Like I was imagining like a little one, like little pieces of wood and stuff. But no, he had like this gigantic thing. And like, how the hell are you gonna start that? And he just bring that like a propane tank with an extension, and he's like, with this. And like, that's so cool. And then we just burned that thing. I was like, wow, I need a farm. So that's it. I used a flamethrower. Well, yeah, that was cool. Okay. Any questions about what we talked about the last couple of days? Same, anyone in the, oh, wait. Why don't this? I'm not reading this. Okay. There you go. Can you hear me now? Yeah, okay. So what we're talking about was a different kind of friction. And there are two kinds of friction that we'll talk about. One is what we call static friction, and the other one is the dynamic friction. So on the static friction, we are assuming that the object is not moving, and the static friction increases linearly with the force that we push. So as we push, the static friction is going to increase at the same rate, and it's going to keep increasing until it reaches a threshold. And at that threshold, the object is going to start moving. And when it moves, then we're going to switch from static friction to dynamic friction. And the dynamic friction is going to decrease. It's a little bit lower than the maximum static friction. And the static friction is constant. And it doesn't matter how fast we go. It doesn't matter. It doesn't matter what velocity you have. Once you start moving, you're going to have this static friction, this kinetic friction. The maximum static friction is calculated by this equation, the mu s times the normal force. And mu s is just a coefficient. And the kinetic friction is mu k times the normal force. And mu k is, again, is another coefficient. It's just another constant. Okay. I think that was the last thing that we were talking about on Friday. So what I want to do today, instead of moving on a new topic, what I want to do is to do a couple of problems involving friction and try to get you, all of you, and in trying that mode of solving the problems. So the way that we're going to do it is I'm going to set up the problem and I'm going to let you do it on your own. And I'm going to let you do it on your own until you get stuck or you finish. And then we'll do it together. And then you can review the project, your problem. Okay. And again, for the people that is online, if you guys get stuck or you want me to, or you have a question, you can just unmute yourselves and unmute yourself and just ask the question. Okay. I'm gonna be walking around the room, so I may not be able to see the chat right away. Okay, so, wow, that was weird. Okay, so this is going to be a little bit similar to the problem that we solved also last week, to one of the problems that we solved last week. So you are helping a friend to move a piece of furniture. Okay. And this sofa has a mass of 30 kilograms. Okay. It has a mass of 30 kilograms. And you are on top of carpet, so you put in one of those little supports on the legs so it can slide a little bit easy. And you know that the coefficient of kinetic friction is going to be 0.8. Okay. And you know that you're going to be pushing this with the force F. Is going to be the applied force. And when you start pushing this couch, it's going to be moving at a constant velocity. Of 0.4 meters per second. Okay, so what I want to find out is what is applied force. Bless you. Yeah, makes sense? Okay, so give it a try. Start with a free body diagram. Identify the forces. Look at what kind of problems are we talking about. Are we talking about static equilibrium, dynamic equilibrium? This is a dynamic problem. And look at what equations you need to solve that. So this is the third time, right? Okay, so I think most of you got the free body diagram correct. So I'm just gonna write it down. So the free body diagram should look something like this. You have basically only four forces. You have the weight pulling down. You have the normal force. You have the applied force. That this is what you want to find out, and then you have friction. Okay, I think most of you got it correct. Now, what you need to find out now is what kind of problems do you have? Do you have static equilibrium, dynamic equilibrium, or you have a dynamic problem? And you have a set of equations for each one of those cases. Like how does Newton's second law changes depending if you have dynamic equilibrium, static equilibrium, or dynamics. And that's the one that you need to write down now. Yeah. Lisa? Access? What you asking?
No, I was just, sorry.
Did you get a message from your sorry?
Yes.
That's fancy. That's pretty cool. Okay, remember you're going to have a set of equations for the x direction, and you're going to have another set of equations for the y direction. Or what is that?
That's just the direction.
Okay, so we have in the x direction is moving at a constant velocity. So that means that we don't have an acceleration. The object is moving, the couch is moving, but it's moving at a constant velocity. So there's no acceleration. So in the x direction, we're going to have that all the forces in x is going to be equals to 0. And this is because we have a dynamic equilibrium. And in the y direction, we have that all the forces are also going to be equals to 0. But in this case, it's because the couch is not moving in the y direction. It's just fixed at the ground level. So here we have a static equilibrium. Okay, so once this is the set of conditions that you need to satisfy. This is the equation that you need to satisfy. So I'm just gonna expand these equations and make them more clear. So what are the forces in x? What are my forces in y? So in the x direction, I only have two forces. I have the applied force and the friction. So the friction plus the applied force is going to be equals to 0. The friction that I have is the kinetic friction, and it's going to be negative. So this is going to be mu k plus u times the normal force times the applied force. That's going to be positive. It's going to be equals to 0. And from there, I can solve for the applied force. And the applied force is just going to be mu k times the normal force. Now, I have the coefficient. I know that mu k is going to be 0.8, but I don't have the normal force. So I need to solve for the normal force. I need to find the normal force. And in order to find that, I'm going to be working with a y component. So in the y direction, again, my equation is all the forces in y is going to be equals to 0. So what forces do I have in y? Well, I have the weight and then I have the normal force. So I have the normal force plus the weight is going to be equals to 0. The normal force is what I want to find out. So that's going to be right. And now the weight is pointing in the negative y direction. So I'm going to have a negative weight. And that's going to be just the mass times gravity. And that's going to be equals to 0. So the normal force is just going to be mass times gravity. Okay. So now that I have this value for the normal force, I can substitute this into this equation. And I'm going to have that the applied force is going to be mu k mass times gravity. Okay. So this will be 0.8 times 30 times 9.8. And I don't know if anyone has that answer. $235.2. Okay, Grace. Sorry, I didn't see your question. So this is friction, F sub R, plus the applied force. And the way we define friction, because in this case, friction is kinetic friction, that's going to be mu k times the normal force. So that's why the normal force appears in the x direction, because this is part of friction. This is how we calculate the friction. Make sense? Yes.
So why did we not use the 0.4 meters per second at constant velocity speed?
It doesn't matter. Like, it doesn't matter what velocity you are. As long as you are at a constant velocity, you will need this force to move at that constant velocity. So in this particular problem, it doesn't matter if I tell you that I'm moving at 10 meters per second or at 0.4. The only thing that matters is that you're moving at a constant velocity. Okay, make sense? Ish? Okay, so we're gonna, yes, friction is negative because it's going in the negative x-axis. Yes, that's correct. So we're gonna do the almost the same problem. Same mass, same coefficient of friction. I still want to find the applied force. But now the couch, at the moment that it starts moving, is gonna go from 0 meters per second to 3 meters per second. And it's gonna take you 2 seconds to reach that velocity. Okay, and the same thing, I want to know what is the applied force to have this change in velocity. Okay, so follow the same steps as before. Draw the free body diagram. Write down what are the equations that you need. Like, what conditions are you dealing with that right now? Is it still equilibrium? Is it dynamics? Is it a dynamic equilibrium? What kind of situation you have? Write down the corresponding equations or the corresponding second Newton's law, like the sum of forces is equals to blah, blah, blah. And then expand that equation, and then follow. Elisa, you were falling asleep. I saw you yawning. But this is exciting. This is physics. It's fun. Well, maybe not fun, but well, maybe a little fun. Now, in this case, there's a change in velocity. So that means that you're going to have acceleration. So this is not going to be equal to 0.
Okay.
Yeah, same thing, but you got acceleration. Yeah, so now you have a change in velocity, so you're going to have an acceleration in x. So that means that the sum of forces in x is not going to be equal to 0. It has to be equal to mass times acceleration. No, no. The forces are still going in the x direction, and the acceleration is going to be along the x axis. So that's acceleration. So, so now in this case you have acceleration dependent on 0. So now all your forces have to be equal to mass acceleration. Now you're dealing right now with now you have the forces in x because that's where you have your acceleration. So the forces in x have to be equal to mass acceleration. Okay, so the free body diagram is going to be exactly the same as you had before. You're going to have your weight, your applied force, your friction, and your normal force. It's going to be exactly the same. And there's really no way that you can tell the difference between this problem and the previous one just by looking at the free body diagram. Now, what is going to be different is that now you're going to have an acceleration in x because you go from 0 to 3 meters per second in 2 seconds. So that indicates there's going to be an acceleration. So that means that in the x direction, all your forces are going to be equal to mass times acceleration in x. In the y direction, again, we're not moving in the y direction. So all the forces in y are going to be equal to 0. Okay, so that's the big difference between these two problems. Even though both are moving, in the first case it's moving at a constant velocity, and the second is moving with an acceleration. So you will have to reflect that on the equation somehow, and this is how you do it. Okay, Emma? No? Yeah? No? Make sense?
Yeah.
Are you sure?
Yes.
Okay. So the acceleration in x, we're going to calculate by change in velocity. So it will be 3 meters per second minus 0 meters per second over 2. That will be 1.5 meters per second squared. Okay, so that's going to be my acceleration. And then I just need to solve the questions. I'm going to start with the y direction first. And notice that the equation between the previous problem and this one is exactly the same. There's nothing that's changing, so we should get the same result. So in the y direction, I have the normal force minus the weight is going to be equals to 0. So the normal force is going to be equals to the weight. And that's exactly what we got on the previous example. Okay. In the x direction, now things are going to be a little bit different. We're going to have friction. Friction is going to be negative. So that's going to be mu k times the normal force plus the applied force. And that has to be equals to mass times the acceleration in x. Okay? And I'm solving for the applied force. So the applied force will be max plus mu k Fa. I can substitute this expression that I have for the normal force here, and I'm going to end up with max plus mu k mg. Okay, you can try to factor out the mass but it's not necessary. Well, this is not gonna. The equation is that long that you can simplify it much. From here, I'm gonna end up with with 280.2 newtons. Yeah. You guys got the same result? So you need 235 newtons to move at a constant velocity, whether that velocity is 0.1 meters per second or 300 meters per second, you need that force. You want to accelerate with an acceleration of 1.5 meters per second square, you need this force, 280.2 meters per second. So if you were to push this couch with this force, 280, you reach to the 3 meters per second velocity, and then you lower your force to 235, you will move at a constant 3 meters per second all the time. Yeah, make sense? Ish? Yeah. Okay. And let's see, what's the next one? Okay. So now we're gonna have a box on a tilted plane. I'm gonna say that this box has a mass of 50 kilograms. Okay, this tilted plane is gonna be a 20-degree angle. The coefficient, the static coefficient between the box and the surface is going to be 0.75. Okay, I'm going to assume that the box is not moving. Okay, the box is static. Okay, so what is the value of the friction force? Okay. So again, draw the forces. Draw a free body diagram. What kind of problem is this? And this is, we only have seen three, so we have either static equilibrium, dynamic equilibrium, and dynamics. Now, in this problem, it's better if you tilt your frame of reference and you make the x-axis parallel to the ramp. Okay, you simplify the math. You wanted to go those?
Yeah, just make those, three angles that we're trying to.
That's not a triangle. So here in your drawing, where does gravity goes? Like that. Okay. So
Oh, so it's gonna be fun.
so the 20-degree angle is going to be this one. Yeah. Oh.
Yeah. I'm just trying to make sure.
So I think most of you got the right free body diagram. So we don't have any applied force. The only thing that we have is friction, normal force, and the weight. Those are the only things that we have. So friction is gonna go in the negative x direction. We're gonna have the normal force along the y-axis, and then the weight is gonna go somewhere around here. And this angle is gonna be the 20 degrees. So again, what I'm doing here is that I'm doing my x-axis parallel to the ramp. So the weight will go there. So it's gonna be somewhere in the fourth quadrant. Friction is gonna go over here, and the normal force perpendicular to the surface. So it's just gonna land along the x-axis. And that's gonna be your free body diagram. Okay. Now, what kind of problem do we have? Do we have a static equilibrium, dynamic equilibrium, or it's just a dynamics problem? Yeah.
Could it be a static equilibrium problem?
Yes, it's going to be a static equilibrium. In x and in y direction, it's going to be a static equilibrium because we want that box to remain fixed. We don't want it to have any kind of motion. So it's going to be a static equilibrium. And then what I need to do is to write down Newton's law. So Newton's law, remember, is force equals mass times acceleration. But in this case, the acceleration is going to be 0. So I'm going to have that the sum of forces in x is going to be equal to 0, and the sum of forces in y is going to be equal to 0. So now what you need to do is to expand this. So work with the x direction and work with the equations in the y direction and expand this equation to try to solve for the friction force.
So this will be the maximum friction. That doesn't, so it's going to be the friction for the development. So, what are the forces you get? So this way, that's the y component, but also you have an x component. Yeah. So, sure. So this is going to be your normal force. And now you're going to, so that will be your equation in y. So in x, what force do you have in x? You have friction. How about this? So the normal force along y. So what you have an x component of force. And those two forces you have to use. Here we go.
Which number is which forces?
So that's the maximum friction. That's not necessarily the one that you have.
It's fine. But, so right now, I think there's a little bit of confusion between the maximum friction force and the friction force and the static friction force. So I'm gonna try to solve this problem and see if it makes more sense. So I'm gonna do the forces in X, okay? And the forces in X, I'm gonna have two forces. I have the friction here, and I have the X component of the weight. So in the X direction, I have friction, and I have the Y component, sorry, the X component of the weight, and that's gonna be equal to 0. Okay? The X component of the weight, that's gonna be equals to mass times gravity sine of 20. And that's gonna be equal to 0. Yeah? Now, I need this. That's my question. What is that friction force? I have the mass, I have gravity, I have the sine of 20, so that's all I need. I don't need to find the normal force in this case. So the friction force is going to be negative mg sine of 20. So that's going to be minus 50 times 9.8 sine of 20. Kelly, yes, I will go through that Vibravec diagram again. So the friction force is going to be 59.8. I get negative 167.6 newtons. And notice that I have a negative, and that's what I want. I want this friction to be negative. Okay, so it makes sense with my diagram. Now, what many of you were doing, you were calculating the maximum static force. So the maximum static force is mu s times the normal force. So what many of you were trying to do is, okay, I'm going to calculate the normal force, and then I multiply by mu s, and then that's going to be my maximum value. And we can do that. I'm going to calculate in the y direction. I'm going to have the normal force plus the y component of the weight is going to be 0. This is going to be the normal force minus mg cosine of 20 equals 0, and you end up with what you guys got? Mary? Emma, I think you got it. You have the normal force?
490.
420?
490.
490. 490 newtons. And then the maximum friction force is going to be 175 times 490. And that's going to be 367.5. So remember, the static friction is not a constant value. It's a value that's going to be changing, and it's going to reach a threshold. So the static friction force is always going to go from 0 to a maximum value. Okay, so in this case, in the case that we're talking, it's going to go from 0 all the way to 367.5. So the one that we found right now is 167. So you can imagine that if I start pushing that box and I start pushing it down, I have a little bit of range before I reach the 367 and the box starts moving. Okay. Did anyone got something different than 50? 3 times 9.8. You still, Grace, I think you still need to multiply by 0.75 for the maximum friction. Okay, makes sense? Ish? Now, I'm gonna go back really quick to Kelly's question. Kelly's asking how did I got these free body diagrams. So I'm gonna do it again. So I have my box, and I have this 20-degree angle. So, okay, so I'm gonna draw my my coordinate axis, and I'm gonna have my x-axis parallel to the plane of the tip plane, and then I'm gonna draw my forces. So I'm gonna have the weight, and the weight is somewhere around the 4th quadrant. They're gonna have the friction, and then I'm gonna have the normal force. So that's the free body diagram. So now what I'm gonna do is I'm gonna draw the free body diagram kind of like with horizontal axis, or with the horizontal and vertical axis. And I'm gonna try to keep the forces exactly how they were. So the friction is along the negative x-axis, so I'm gonna go like that. Normal force is along the y-axis, and the weight is gonna be in the 4th quadrant. That's gonna be the weight, and this is gonna be the 20-degree angle. Makes sense, Caleb? And apparently I made a calculation error on the previous problem. Oh, yeah. So here, so in this problem, this part, mg cosine of 20 is gonna be 460.4. And here, when you multiply by 0.75, you're gonna get 345.3. So okay. Yeah, just make sure, Emma, just make sure to check your calculations. Makes sense. So we'll work a little bit more next class also with problems involving statics. They're kind of tricky, and it's kind of confusing when is the maximum friction and when is somewhere in between, and so, but it's just practice, and hopefully we'll get it right. Yep. Any questions, anyone? Yes.
For this kind of problem, we don't have to solve for the x direction because that's just 0.
For in this problem, you actually don't need to solve for the y direction. You can just go directly through the x direction, and then you will get the friction force.
Okay.
Yeah. If you were to calculate the maximum force that you can apply, then you will need to use the y direction. Okay. Celia, go. Mary? Any questions? That was very aggressive. Just a little bit. I guess you're a little bit tired. Shall we go? Yeah. Yes? You sound too excited about leaving my class.
I'm hungry.
Me too. Okay, let's go. Have a good day, everybody. See you on Wednesday.
I was in reading, so that's awesome. When do we realize it?
When you want to calculate the maximum static force,
Which we didn't have to do.
which you don't have in this case. we'll do a problem when you actually need to calculate the maximum static.
Trying to get time for them, though. If I come back to get really tomorrow, so I don't know then. That doesn't come out.
Thank you.
You're welcome.
Yeah. Yeah, and I understand how we got these and these. But then.
Keenan,
Yes.
I need to talk to you
Yes.
real quick.
It's not.